So today I'd like to talk a little bit about exponential growth and decay in terms of real world problems. You spent a lot of time studying exponents, and in Algebra 1 and in Algebra 2 you studied quite a bit with what exponential growth looks like graphically, but these are some real world problems where we're going to look at real world scenarios where the growth tends to be exponential. So as you read along in your notes, you'll notice that this type of exponential growth might apply to money or how bacteria grows, how disease spreads, how radioactive things might decay, or how population in certain cities or countries or towns tends to grow. So one of the formulas that you'll need to be able to use, you don't have to memorize any of these formulas, you just have to know what they mean and how to use them, is this exponential growth formula. And let me just explain each part. This number right here, n, that represents the final amount. So what you end up with after the growth occurred. This number right here that looks like n sub 0 is actually read as n naught. And n naught is the initial amount, what you start out with. R represents the rate of growth or the rate of decay. That could be positive if it's growing or negative if it's decaying. And finally, the exponent, the most powerful part of this entire thing, is t for time. So that's your general formula for any type of exponential growth or decay. Now, when we get into money, money sometimes follows, well, actually quite often follows a slightly different type of exponential growth with the invention of compounding. So with money, we tend to find that money grows in a compound way, which means that the interest you have earns interest. And then the next year, you earn interest on that new amount. And then the year after that, that new amount you had earns interest on that. And it keeps growing that way. So we have to tweak the formula a little bit. And this is your compound interest formula. It's very similar. Instead of n, we use the letter a, but it still represents the final amount. Instead of n naught for the initial amount, we call it the principal, but it's still the amount you start out with. R still represents the rate, and that's your annual percentage rate, what your percent in interest is each year. T stands for time, but you'll notice the introduction of this new variable that appears twice, n. N is the number of times you're compounding. So, for example, if your interest is being compounded monthly, n would be 12. If your interest was compounded daily, n would be 365. So I think the best way to attack today's notes are, now that you kind of have an idea of what the formulas are and what each component means, I think you should try problem 1, arrive at an answer, and then come back to the video and check to see how I did it and see if we match up. So let's take a look at number 1. Why don't you read this, pause the video, and then come back. Hey, welcome back. I hope that you tried the problem on your own, and let's see how you did. We see that we have bacteria that's growing at 35% every hour. If the population starts out with 100 specimens, how many are there after 6 hours? Well, let's take a look. I chose this equation because we're not dealing with money. I don't know what our final amount is, so I kept that as n. I do know what our initial amount was. Our initial amount was 100, so I put 100 there. Remember, R stands for the interest rate. I don't want that as a percent, I want that as a number, so I converted the percent into a decimal. And of course, the time is 6 hours. And so after 6 hours, we end up with about, notice the wavy equal sign, 605 bacteria. Well, that seems like a lot, but really, in terms of bacterial growth, it tends to be a lot faster than that. Let me show you an example, a real-world model of bacteria growing, and let's see what you think. So here we go. Let's take a look. This bacteria is simply doubling. Every 20 minutes, this bacteria is doubling. And it doubles every 5 minutes. And after an entire day, you get over 5,000 million bacteria, which is pretty gross. But anyways, that's how bacteria grows. It grows exponentially. Let's move on to problem number 2. Why don't you take a second, try this problem out, see how you do, and then come back to the video and see what happened. Okay, welcome back to the video. Let's take a look at what we have going on here. I started out with this formula. This is the basic formula I chose. I asked that every time you do a homework problem, you show me the formula you're using so I understand, first of all, foremost, if you understand the formulas. Let's fill in what we know. We know that the beach ball originally had 4,000 cubic centimeters, so I put in the 4,000. I don't know N. I know that the amount of time is 5 days. Let's talk about the rate though. Notice the ball is losing 6%, so I entered that as a minus 0.06. I typed that in my calculator. That's about the volume of air that's left after 5 days. It has not quite lost half of the amount of air. But there's a follow-up question to this, and the follow-up question is pretty interesting. In how many days will it take the beach ball to lose half of its air? And then will there ever be a time left when there is no air left in the ball? So let's talk about this. This is a great example of exponential decay. It's not growing because the rate is negative. So this time I chose the same formula, but let's see what we filled in. Well, I know the initial amount was 4,000. I know that it's losing 6%, but I don't know the time. So this time I kept t as the variable. I do know this N value. The question is, how long will it take to lose half of its air? Well, if it started out with 4,000, half of that would be 2,000. So solving this is a little bit tricky. Notice that the variable's trapped in the exponent. So the first thing I did is I cleaned this side up and I got rid of that 4,000. So we are right there. 1 minus 0.06 is 0.94. And then this 4,000 I divided on both sides. Now, right now, we don't have the tools we need to solve this, but let's take a look at how else we could solve this. But I'll give you a hint. It involves logarithms. Let me go to my trusty calculator. So there's my calculator. I think in order to solve this, I might just enter these numbers into my calculator. Let me graph 1/2, 0.5, as one of my y values, and I'll graph 0.94 raised to the x as my other. Now before I hit graph, let me pick a decent window here. My x minimum, well, I'm not going to have negative days, so I'll go 0. How many days do I think it's going to take for this ball to lose half of its air? Well, up here in problem 1, it took 5 days and it didn't go to half. I'm going to guess 20 days. Who knows? And I'll count by ones. That's fine. Y minimum, well, again, we're looking at 0. Y max, well, I know that my 1 value here is 1/2, so I'll just say Y max of 1. Let's take a look at this graph. So there's my first graph, the left side, the 1/2, and here comes my exponential decay. This is that ball losing air. Aha, and I see that point right there is where they meet. So what is that value? Well, I could go to the table and play around and try to get to the table, but the calculator has this beautiful calc feature, and I want to calculate the intersection, option 5. There's my first graph, there's my second graph. I get close to the intersection and it tells me, well, this is going to happen in about 11.20 days. So I asked, how many days will it take? I should probably round that. And if you think about it, I think the rounding needs to go to 12. I didn't answer the second part of this. That's something we'll discuss tomorrow. So give that second part some thought. Meanwhile, let's move on to problem number 4. Problem number 4, this time we're dealing with some money. Why don't you read this, try to answer it, and then pause the video. Hey, welcome back. Let's see what you set up for this one. First of all, I chose the compound interest formula. And let's fill in the parts we know. We don't know how much money we have. I know the initial principal is $1,000. I know the interest rate is 4.7%. Again, remember, that is a decimal. Now compounding this n value. This n value in this case, since we're compounding monthly, is 12, and the time is 2 years. This is a problem I can just dump right in my calculator and get the final amount. Let's try problem number 5. Number 5, we have a case where we're involving 2 people here, and we want to see who's got the more money in it after a while. So let's take a look at Danielle, and let's take a look at Charlie. Both going to use the same formula. Danielle puts $2,000 into her account. Her rate is 5%, but she's compounding it daily, so there's 365 days in a year. And of course, that's for 15 years. So Danielle ends up with that much money. Now, how did her old special friend Charlie do? Well, notice Charlie has some different numbers here. He is compounding annually, so that's why the n value is 1. It didn't even show up. And Charlie ended up with more money. Well, why did he end up with more money? Well, if you compare these side by side, although Danielle is compounding more, and although her interest rate is higher, it's the fact that Charlie started with way more money. A lot more money. And we'll see how that has an effect later on tomorrow. But in this case, Charlie ends up with more money. Maybe he'll be a good special friend and loan that to Danielle. Let's take a look at this next one. And about how many years will Danielle's account have more money in it than Charlie's? Well, this is one I want you to give some thought to. Play around with it and see what you end up getting.